So welcome back. All right, in this second segment, I want to talk about what's known as Bayesian optimization. I only write optimization here on the first slide, but most people call this Bayesian optimization. I try not to use the word Bayes too much in my talk because I don't think it's essential to even understand what that is. What we're going to do is we're going to use Gaussian processes to assist in optimizing a function that's of interest to us that we don't know very much about. So we just talked about how to model functions given example realizations. And now we're going to use those models to try to find the input settings that optimize some aspect of that function, like to find its minimum or something like that. So that's what this segment is about. Of course, we're using optimization under the hood in the Gaussian process to learn its hyperparameters. And now we're going to kind of turn things around on its head and use those fits to help optimize other functions. So I'll get into exactly how that's going to work in the next few slides. Okay, so the goals here are to understand the role that Gaussian processes can play in optimizing a black box function. So what does black box mean? That means you don't know much about how that function is composed. It's opaque to you. You get to evaluate it, but you don't know much about what it does under the hood to provide the output that it gives you. Okay, so the only way that you can learn about how that function behaves is through presumably expensive evaluation. So I think about it as running a computer code. And evaluating the function engages a computer, maybe a supercomputer, and I get the output f of x, y equals f of x, after great computational expense, maybe in money and in time. Okay, so the idea of Bayesian optimization is to view optimization as an application of what the machine learning community calls active or reinforcement learning, or what the statistical community calls sequential design. So the idea is to kind of build up knowledge of the thing that you're working with, the thing being the black box function, and use that knowledge to make informed decisions about the answer to the question, which is where is the function minimized or something like that. So to try to create this virtuous cycle between data acquisition and problem solving. And here, in this talk, the problem that we're trying to solve is to optimize this function. In reinforcement learning, there's usually some other kind of goal. You want some robot to behave in a sensible way, which you might be able to frame as an optimization problem too, but perhaps it's more nuanced than that. The role of modeling, that's what we're doing. We're using Gaussian processes as a model, has a rich history in the optimization literature, by which I mean like math programming literature or operations research literature. Here, we're not going to talk about that in any systematic way. We're going to just look at the potential role of modern statistical modeling, Gaussian processes, in the enterprise of logistics or machine learning or anywhere optimization is involved. What I like to call what we're going to do is surrogate-based optimization, but if you want, you can write a Bayesian optimization, same thing. Okay, so I think that this is an old idea, but it has been approached from a new angle in the last 10 or 15 years. So statistical methods and optimizations goes back to a famous set of papers by Box and Draper, who are kind of household names in statistics. And there are whole books written about this in the 80s. I'm not going to give a list of those books. I don't even think you're interested. What I'm going to describe to you was first written about in the 70s, but it was largely ignored. So this paper from the 70s was called The Application of Bayesian Methods for Seeking the Extremum. This is where the word Bayesian comes from in Bayesian optimization. Again, I don't think that you need to understand what Bayesian means to understand what we're going to do. Okay, so these ideas have been revisited in the last 10 or 15 years, And the reason why they're popular now, and they weren't popular in the 70s and 80s, is because the Gaussian process wasn't popular in the 70s and 80s. So we now do these things, these ideas from the 70s, with a new model, because that model has so many nice properties, as we saw in the previous segment. Okay. The best reference, if you're looking for one, for the core idea of what I'm going to describe now, is this paper from the late 90s. They called it surrogate-based optimization, but like I've been saying, it's basically the same thing as what many people now call Bayesian optimization. I think that the authors of this paper in 1999 were not aware of that 1979 paper, so they didn't use the same terminology. But since people have started to adopt that older nomenclature. All right, so here's the algorithm, three-step algorithm in a for loop. So here's the idea. You train your model, Gaussian process surrogate, on the example evaluations of your function that you've obtained so far. So just like what we did in the first hour and a half, you collect some data and you build a model fit for that data. And now your goal is to optimize the function, so to find its minimum, say. So what you do is, instead of optimizing the function, you optimize the surrogate. You like move the problem, right? The problem is you want to find the optimum of the function, but the function is expensive to evaluate. So you evaluate it and fit a model and optimize that instead. This is where the word surrogate comes from. You're using the model fit as a surrogate for the real thing. And then that gets you the next spot where you're going to evaluate the actual function. Then you evaluate the actual function and what you think is the answer, what you got from the surrogate, and then repeat. So the idea is that this auxiliary thing is providing you with some information that's similar to what you would get if you did the real function evaluation, but not the same. Observe that this step 2 here involves its own inner optimization. We're optimizing the surrogate in order to help optimize the real function. The idea here is that the surrogate is cheap to evaluate, and you can do that as much as you want. The thing that you want to avoid is evaluating the real function. Okay, so that's sort of a warm-up. I want to be crystal clear about the problem. It's kind of, I think it's always kind of awkward when someone describes a situation in words and never writes it down in concrete mathematics. So here it is in concrete mathematics. I have a function f, and I want to know its minimum. I want to know x star. What value of x minimizes that function? And I have some study region that I'm calling B. I'm thinking about it as a box. So in that study region, maybe it's a hyperrectangle. I want to know what value of x minimizes it. But I don't know much about f of x. In particular, I might not have its derivatives. Even if I did have them, I might not necessarily want them. Derivatives are not always as valuable as you might think they are. They were in the previous segment when optimizing hyperparameters, but in general, derivative information is not always helpful. And because I don't assume that I have any derivatives or really know anything about the function, the methods that I'm talking to you about fall under what the math programming community, this is a mathematical program, right? This expression. This is what the math programming community calls derivative-free optimization. And there are lots of nice books that cover non-statistical methods of solving problems just like this. So all we get to do is evaluate the function. For now, I'll assume that the function is deterministic, but very expensive to evaluate. So this is where the learning comes in. I'm going to get some pristine evaluations of my function, but presumably I can get very few of them. So I'm not going to be able to explore what f looks like for all possible x that I might want. I have to be very frugal. So there's actually, I like to think about it as a constraint. There's a constraint on the solver, not a constraint on the system. The system for right now is unconstrained. I want to find the function, the value that minimizes the function, regardless of anything else that's going on. But I want the solver itself to limit its evaluation of the function. So I have a constraint on the expense of the solution. Okay. All right, let's do an example. I want to start with an example. I'm going to write down a function, and it's not a black box because you can see it. There it is. I mean, maybe you're not good at reading code, and it might as well be a black box to you, which is fine, because I don't want you to look at it too carefully. I want you to see that it's a complicated function. It's nonlinear, and it's in 2 dimensions. It's called the Goldstein price function. So this is a function of 2 inputs, and it actually has many local minima. And I want to minimize this function. And we'll pretend that we can't see it. We're just going to evaluate it. We're not going to use any other information about the function except for its evaluations. Okay, now I want to execute the idea that I wrote in pseudocode or in a bulleted list on the second slide, I think. So I'm going to evaluate the function at a small number of inputs in the input space kind of uniformly. So I'm going to take 12 inputs to start with. And what are those inputs going to be? They're going to be random. They're not going to be completely random. I don't want to get into what an LHS is, but for right now, let's just assume that it's random. So I'm going to take some random inputs, X, 12 of them, and evaluate my function at those 12 inputs. So those data examples represent our body of knowledge about the function at this time. And I'm going to fit a Gaussian process to those examples. And I'm not going to cut and paste stuff anymore. I'm just going to use library routines to do that. So I'm going to build a Gaussian process and do the MLE calculations for its parameters. So it turns the whole thing into a 2 or 3 line bit of code. Okay, so I'm using libraries to do the fitting. All right, so now what am I going to do with that fit? I'm going to do the second step in my algorithm. That second step is to optimize the surrogate, the prediction from the fit rather than from the function. So I'm going to set up an objective. I'm calling this objective my mean. It's a function that I'm going to optimize instead. What am I going to optimize instead? I'm going to optimize the prediction from my Gaussian process. What aspect of the prediction? The mean. My Gaussian process will give me a mean and a variance. It'll also give me a covariance if I want. But all I'm going to use for right now is the predictive mean. So I've created a function that is my new objective. It's kind of a trivial function. It just allows me to evaluate something to return the mean from my fit. And that's what I'm going to optimize instead. So I'm going to put into the optim function this objective. That's the important thing here. I'm going to optimize. What am I optimizing? This is the new function I'm optimizing. The optimizer has to have a place to start. So I'm telling it, start your optimization at the previous best solution in the data set. The previous best solution in the data set is the one that minimizes the y values that I have already. And it comes back and says, this is what I think the minimum is. So in the 2-dimensional space, those coordinates represent what the model thinks is the minimum. So this is the next point to try. Let's look at a visual of that. Okay, so here's a cheap visualization. Each one of the open circles on this plot is one of the 12 input locations that I use to evaluate my function, my expensive function. I'm not showing you the y values because I don't think those will be too useful. These are just the 2 inputs, the 2 pairs of x values. This one right here is the best so far. That's the one that has the smallest y value. I ran an optimizer of the statistical model starting at that location and asked it, where does the statistical model think the function is minimized? It thinks it's minimized there. That may not be where the function is actually minimized because the statistical model might be wrong. In fact, it's almost surely wrong, but it might yield something that's better than what I had before. Okay, so now this is the point to try. I'm being frugal about evaluating the real function, but now I have a good place to try. And I'm going to try right there. Okay, so I try right there. I run my function, my expensive function at that location. and then I can use that new information to update my fit. So now I've learned something, right? Even if I was wrong about where the function is minimized, even if I was way off, I still learned something. I've got more information about how f works. So I can update my fitted response surface. I can update my surrogate. And the next time, no matter what happens, I've learned something. And I hopefully can parlay that into a smarter decision next time. So here's my next smarter decision. I'm going to optimize. Again, this is cut and paste now. I'm optimizing the same objective, but now it's been updated to incorporate the new information from the previous evaluation. And I'm going to ask what to do next. This is the point that I want to evaluate next. Let's look at that in a picture. Okay. So you'll notice if I go back here, there's no open circle here, but this is where I'm going to evaluate. When I go 2 slides ahead, I've got an evaluation there, but this was not an improvement on my best minimum because the best one is still here. This is where I'm still searching from. And now I search a little bit in this direction. That's where my surrogate now believes that the function is minimized. So it was wrong, but it learned something and it's revised what it believes. Okay, so I don't want to keep doing that one step at a time. I'm going to fast forward a little bit. I'm going to take this idea and put it into a loop. It's actually a while forever loop, but that loop is going to stop when the recommendations from the model are not changing relative to the truth. Or not the truth, relative to the evaluations that came from the data. Okay, so it's not really going to run forever. It's probably only going to run for like 10 or 15 more iterations until it's confident that it has converged. Okay, and here is a summary of the progress of that loop. So the loop actually starts here at 12. So this x-axis is counting the number of evaluations. So I did 12 to start out with, and the value of y that minimized the function was this one. It was -2.5 or something. So -2.5 was the best output value of the function I was trying to minimize at the start. And for the first few iterations, it doesn't improve upon that, but then it does. Eventually, it gets down to -3. So it's found some part of the input space where the function is minimized, and it stopped because it wasn't able to make any more progress on that algorithm. So it deemed itself to have converged. So that's the idea of the algorithm. The fitted response surface, the Gaussian process, is being used as a surrogate for the expensive function so that it can make a decision about how to use that expensive function in a frugal way to find the value of x that minimizes it. Okay, so here is that idea wrapped in its own function. So I've taken all the code we've used so far. It's basically just this while loop that we did, but I've put it in its own function. I called it optim_sur. It takes an f. It takes a number of points to start with. It takes a number of points to stop with, and it has a tolerance for stopping early. This is just to prevent it from running longer than you want it to. Like maybe you have some total budget, right? Somebody tells you, you can evaluate the function 100 times, but don't do it 100 times if you don't need to. Stop early if you meet some tolerance. So that's the idea. I want to minimize this function f, start with 12 maybe, stop with 100, or stop even earlier than that if you don't need to do all 100. And then the rest of it is all the code we saw already pasted into the function. So it's only like I think that might be like 20 lines or something. The whole idea is wrapped into 20 lines of code. Why am I doing this, putting it into a function? Because I want to explore the average case behavior of this idea. I want to be able to run it over and over again to see how it behaves empirically. Okay, so that's what I'm going to do. I'm going to do 100 of these optimizations of the same function f, starting with 12 and doing as many as 50 evaluations, maybe fewer. And I want to see what answers it gives me. Now, the starting 12 is always random. So the way the thing is initialized is what's uncertain, where the variability is going to come from. The algorithm is not making random decisions. It's making very purposeful deterministic decisions. It's using statistical uncertainty in that decision-making process because it's fitting a statistical model and extracting its predictive mean. But each decision that it's making is not random. It's deterministic. It's just the whole thing is seeded in a random way because the initial bunch of 12 points comes from this random smattering.
May I ask a question on this?
Yes.
Does the inclusion of a nugget of the additional uncertainty on the surrogate model, does it affect the mean that you're trying to optimize at every iteration?
That's a good question. The answer is yes. So if I'm using a nugget to smooth rather than interpolate, that will affect this algorithm. However, for this example, I am not fitting a nugget. I am fixing a very small one and treating the evaluations as deterministic. Okay. So I could work with random function evaluations instead, which is a harder optimization problem. Then you have to be a little bit clearer about what you want. Are you trying to minimize the mean of the function or what? But you can do this idea with noisy evaluations too.
I see. Okay, thanks.
Okay, so I'm being clear about this decision-making being deterministic because some people incorrectly characterize what I'm describing as stochastic optimization. An example of stochastic optimization is like a genetic algorithm or simulated annealing. Those are two stochastic optimization methods. They make random decisions. This is not making random decisions. This is randomized, it is initialized randomly. You don't have to do that either. You can initialize it deterministically. I'm just initializing it randomly because I want to see what its typical behavior is. It is not a stochastic optimization. It is an ordinary deterministic optimization. Okay, so here is the behavior of each one of those 100 optimizations. Up to 50 iterations. Some of the methods used all 50. Most of them did not. Some of the methods converged to an answer around -3, which appears to be the correct answer. That's about as low as we can go. But other methods get stuck and converge to inferior local minima, like at -2 or -1.75, or maybe this is -0.75. So it's clear that this is not a global optimization tool. It's probably finding local minima, but may not always find the global minima. In fact, we know it doesn't always find the global minima because we see examples of solutions that are inferior to other ones that are better. So maybe this isn't the best optimization, but now I want to try to convince you that it's a good one in the spectrum of optimization methods for a problem as challenging as the one that we're doing. Okay, so how does it compare to something else? R has built-in optimization libraries. We've been using them for the first hour and a half. So why don't we ask how well it does on these problems, or a problem like this one. Unfortunately, the optim function does not accurately count the number of evaluations of the function, and it also doesn't save those evaluations. And I needed to do both of those things in order to compare it to what we just did. Now we're operating in kind of a unique framework where the number of evaluations is really important. That's the thing we're trying to cut down on. Whereas conventional optimization tools worry less about that. Although often they have maximum number of iteration arguments, most of them determine whether or not they stop exclusively on convergence criteria. and they don't save all the evaluations in the middle. And that's what we want to see. I want to see what our progress is. I want to make a plot like this, but for Optim. So I'm doing something that would maybe be non-standard. I've written a different function that I'm calling f prime, which evaluates f, but also saves the previous evaluations. That's all. I just don't want you to feel like I'm doing a sleight of hand here. I'm optimizing a different function. I'm going to optimize this thing I'm calling f prime, but it's really just f, except it's saving the previous evaluations so I can show them to you after the fact. So I'm going to do the same loop of 100 random restarts of a deterministic optimization algorithm. I'm going to use BFGS because I think that's the best method. BFGS approximates gradients through finite differencing. So some of the evaluations that it does will be spent on approximating those derivatives. And that's going to be one of its major crutches, because our previous method did not need to spend any evaluations approximating derivatives. It was getting a sense of derivative for free through the surrogate. Okay, so here's my loop, my 100 reps of Optim. Here I'm calling Optim. Each time I'm randomly initializing it and giving it this function f prime and asking it to do BFGS. Optim does have an advantage over what we did previously in that it doesn't need to start with 12 points. Our other method doesn't need to start with 12 points either. It could start with fewer. But here, one of the advantages of this Optim method is it's only starting with 1 point, a pair of coordinates in the two-dimensional space. So it gets to make more decisions earlier. But even though it's allowed to do that, it does not do as well. So each one of the red lines is a solution trajectory coming from the Optim method. You want to be as close to the bottom left-hand corner as you can in this plot, because it means that you're making faster progress with fewer evaluations. But you can see the progress is slower. It's taking more evaluations to make progress. And as a function of the number of evaluations, it plateaus. In each stage of the algorithm, it has to do 4 evaluations of the function just to approximate a derivative, and a 5th evaluation to decide whether it's made progress. So in each round, it's actually sampling the function 5 times, whereas ours is only sampling the function once. I think that most of the advantage of the surrogate method comes from that. It comes from not approximating the derivatives. Or you could say it's approximating the derivatives without extra evaluations by using the whole fitted response surface from all of the data that it's collected so far.
We have one question on Discord, if I may interrupt here.
Yes.
And it is it better to randomly choose initial points or choose equally separated points? And what are some optimal initial point choosers?
That's a good question. So there are some very nice papers that show that random is very good. So starting out randomly is good because it gives you a random set of pairwise distances. And those pairwise distances are what help in learning. If you have a diversity of pairwise distances in your training set, then you learn the hyperparameters like the length scales and so on more accurately, and therefore you make better earlier decisions. However, that is not optimal. There are optimal designs that ensure that you have enough random pairwise distances. Random doesn't ensure that, it only guarantees it on average. Anything you do random has some pathological case where it's really terrible, right? But you can optimize the principle of that to ensure diversity of pairwise distances, which will always work well for you every time. The thing that you don't want to do, and I don't know if this is what you were suggesting or not, you don't want to spread the points out in the input space. This is counterintuitive, but if you try to spread them out, like maybe try to maximize the minimum distance between the initial points, that might seem like a good idea because you're spreading them out, but that's almost pathological from a Gaussian process perspective because it ensures the opposite thing. It ensures that you don't have a diversity of distances. By maximizing the minimum, you make it so that there are even fewer small distance points. And it might be small distance points that are really important for learning the curvature of the function. I don't know if that helps, but the answer to your question is yes, but it's nuanced.
Seems that this topic, Cameron, who asked the question, is thanking. I guess that is a satisfying answer for his point. There are other people that are also writing. John is asking, how about hypercube selection for high dimensionality? I think this is quite a rich topic. Would you like to comment?
I think what you're asking is, how do you choose the study area? Like, how do you decide where you're going to search for an answer? I don't know the answer to that question, if that's your question at all. I haven't thought too much about that. I can imagine, though, that in practice, that's a very important, maybe pre-processing step in this whole enterprise, and I don't know how you do it.
Okay. John says, no, he means for the selection of the training data.
Oh, I see. I mean, what I would do, what I think works really well, is just take the study area and decide to randomly choose the initial points. And then the question just comes down to how many. And the rule of thumb that most people follow is that you should have 10 for each input direction, which is actually more than I did in this problem. I had 2 input directions and I did 12. So I did fewer than what most people would recommend, and it still seemed to work pretty well.
Okay. Yeah, I think some of this discussion goes towards low discrepancy sequences, maybe.
Could be, and I think I might not be your guy to talk about that.
And maybe we keep going from here.
Yeah. All right. So we've talked about this already. Why did our method do well compared to the conventional optimizer? One is we don't approximate derivatives, or the sense in which we do is much different if you want to argue that we do. We're getting a sense of derivative and a lot more besides for free. Also, we can take potentially big steps in the solution space because our knowledge of the response surface is more global. Optim, using BFGS or any of the other methods that it uses, is maybe going to do a line search away from the current best answer in order to make its decision. It's not going to entertain finding answers anywhere in the entire search domain, even though it may eventually get there. Okay, so that's why we do well. How can we do better? What I just presented to you is the tip of the iceberg for using a surrogate to guide an optimization. There are many ways in which we are doing, in which what we are doing is inefficient. It's a little bit greedy, so it exploits by moving to the next best spot from where it left off. So it's not using all of the potential it might have for having a global perspective. And it's doing that with its own Optim subroutine on the predictive surface. It does not explore places that cannot easily be reached from the current best value. But those are all minor things. What we really want is some automatic way to balance these two things. So I put exploits in italics and explore. When you talk to folks in Bayesian optimization, they're always trying to find the right way to balance those two things, to make an optimizer that can decide, do I want to take a chance or do I want to take advantage, right? That's how I see these things. Explore is take a chance, exploit is take advantage. And to make a decision criteria that can decide when to do which of those things. And in answering that question, I always like to point out the following, which might already be obvious to you. We're not actually doing statistics, at least not in our decision making, because at no point is uncertainty being taken into account. Uncertainty is key to statistical enterprises, right? Otherwise, you're just fitting or tuning. But until you look at sigma squared, whatever you want to call it, until you start looking at variances in some way, then you're not really making a statistical decision. And we're not. We're only optimizing the mean. We're not taking uncertainty in that mean into account. So I think the way in which we can do better, potentially a lot better, is to try and come up with a criteria that looks at both things simultaneously, that looks at the mean in order to exploit and looks at the variance in order to potentially explore. So that leads me to the next topic, which is called expected improvement. This is the main technique that people use to synthesize both pieces of information. So the idea is to strike a balance. And the idea comes from a PhD student at the time, he's not anymore, named Matthias Schoenlau. He was working on his dissertation in Canada, I think at Waterloo in Canada. And he was looking at Marcus's paper, the one that from the 70s that I introduced at the very beginning. And he was trying to port some of the ideas from that paper over to the Gaussian process framework. And he came up with this heuristic that's now called, what he called it, expected improvement. And he came up with an algorithm based on that expected improvement that he called the efficient global optimization algorithm. So if you've seen these two things before, they are the same thing, really. People don't usually talk about ego much anymore. The algorithm is based on the heuristic. They just talk about the heuristic. So if you hear people saying they're doing efficient global optimization, they probably mean they're doing an expected improvement. I see them as the same thing. One of them, the name of the decision, the other one, the name of the algorithm that comes from making that decision over and over again. His key insight was exactly what I put on the previous slide, that predictive uncertainty was underutilized in the surrogate framework for optimization, which is especially a shame when Gaussian processes are used as surrogates because they provide such beautiful predictive variance surfaces, because they give those sausages. The sausages really capture what's going on when mean compares to variance. The idea that he had is not limited to Gaussian processes, but I think it's particularly a shame if that's what you're using. Okay, so here's the idea. He developed a statistic, a random variable really, that's called the improvement. So here's the improvement. A location in the input space X represents improvement if its predicted value, so this is what we get from the Gaussian process, right? If its predicted value is below the current minimum. So if this is what you currently believe the minimum to be, that's the definition down here, the smallest y value you have already. So if you have high mass below that value, then you have improvement. Remember, this is a random variable. It has a Gaussian distribution. We developed that in the previous slide segment. So some part of the distribution of this random variable is below this value, and so it has some improvement. The zero here, I like to think about the zero here as a mathematical trick because it's a random variable. This is either a zero or a difference, but in aggregate over all the y values, it's always non-zero. There's always some potential for improvement because this has a Gaussian distribution. So some part of the mass of its Gaussian distribution is below the current best value. The question is, how are you going to use this quantity since it's a random variable? And the way that Matthias Schoenlau decided to use it is in expectation. He took an integral of this quantity and called it expected improvement. So if y of x has non-zero probability of taking any value on the real line, then this improvement has non-zero probability of being positive, and its expectation is also positive. So every point has potential for expected improvement. Just some of them have more potential than others because some of them have more of their mass below the current best value. So he talked about expected improvement. He wrote down an integral and he solved it. But before we write down an integral and solve it, I want to remark that you don't need to be a fancy integrator to use this expected improvement idea, because you can always integrate with Monte Carlo. As long as you can draw from the predictive distribution, and that's what we spent most of the last lecture doing, drawing from the predictive distribution and making plots, we can always evaluate the expected improvement through an empirical average. I can replace the integral with the sum. I can basically count the number of times I get improvement. And each time I do, I can measure the amount of it. And that's my expected improvement. So this is an idea that you can do even if you're not using a Gaussian process. Anything that you can get predictions from, where you can sample those predictions, you can calculate this idea of expected improvement. He showed that when it's Gaussian, you can do it in closed form. So you can take that integral without Monte Carlo, and it has a really interesting formula. This is the formula on the slide. Looks a little complicated, but when you look closely at it, it makes sense. It has two distinct parts. It has, I'll call this the explore part, and sorry, this is the exploit part, and this is the explore part. Why am I saying that? The first thing I'll ask you to do is to kind of ignore these two numbers, the one inside the capital phi and the lowercase phi. That's the Gaussian CDF and PDF. Just in your head, write A and B. Maybe I should do that on future slides. It's A parts of this thing and B parts of that thing. So the important thing being the part here and the part here. What are those parts? This is the mean. That's what we were optimizing before, right? Before we started getting into this expected improvement mess, we wanted this to be as low as possible. And it's got some part of the standard deviation. So it's already using more information. It's using uncertainty. So it's balancing mean and standard deviation. The weights in that are a function of some other quantities. And I don't find those to be that intuitive. And those trade-offs depend on things that also involve means and variances in some way. So it's a balancing exploitation in the mean and exploration in the standard deviation. What is intuitive is the way this looks when you plot it. So this is what's on the next slide. I stole this. This is the first thing in all these slide decks that's a picture that's not based on code. This was cut right out of the paper that describes this for the first time. I felt like I could get away with this because in a minute, I'm gonna do a live demonstration. But first, I'm gonna show you the picture because I don't know if you can improve upon this very much. So here's the idea. The function was evaluated 5 times. Here's 4 evaluations and there's a 5th one right here. The Gaussian process was fit, and this is the mean that it goes through the points. That's the fitted mean to the Gaussian process. They chose not to show the error bars. Instead of showing the error bars, they showed the standard deviation function at the bottom. So this is the uncertainty. The uncertainty is low over here because there's a lot of training data. It's high in the middle because there's no training data there. And then it's low again nearby the final training data point. So this is like the sausage, right? But it's not showing you the error bars, so it's missing the other half of the sausage. Okay, this I really like. This is a Gaussian PDF turned on its side. But this is what the uncertainty looks like. If I want to make a prediction here at this point 8, that in the input space, I predict it to be y there, right? 8, that's also 8, coincidentally. So I predicted at 8, but my uncertainty is large because I don't have any data nearby. And in fact, some of that uncertainty is below my current best value. This is the current best value, and some of my uncertainty is below it. So this point has potential for improvement, just not a lot. The idea of expected improvement is to synthesize those two pieces of information. And that's what's being shown down here. Expected improvement is high, where the mean is low, and also high, where the variance is high, even if the mean is not low. When both things are happening, it's even higher, right? So this would recommend taking the next point there. You would maximize expected improvement. That's what you want to do. So you're trying to minimize the function, but maximize this piece of information, this expected improvement. And so you choose to sample here next, and that's what they get there. And that sort of squashes down any potential for more gain in this area. And the next thing to do is explore, to see what happens here, because we don't know if it's going to be high. I mean, we could get a point down here. We just don't know. And this distribution says so. We could get a point down there. We believe it's low probability, but it's worth checking in on. Okay, so the next thing I want to do is a little demo. So this was provided in the course materials on the Dropbox page. I have to stop sharing. Let's see, stop share. And I'm going to share something else in just a second here. Give me 30 seconds. Share screen. All right, so if I did it correctly, you should
Yep.
see my R environment.
We
So
do.
good. All right, the code itself doesn't matter too much. I'm going to make it, I don't need you to see the code. I just need to run it. You can check on the code if you want. Let's just do source. Okay, and then I'm going to make it so that more of the screen shows the picture. Okay, so this is our favorite sign example from the last segment. So I've evaluated the function at 1, 2, 3, 4, 5, 6 locations, and I've fit a Gaussian process to it, and I've shown you the mean surface in black and the error bars in red, and then each of the gray lines is a potential realization. On the bottom is my expected improvement. So I've run through that calculation, balancing mean and variance for all of the input spaces from whatever, this is -1 to 7 or something. And I plotted the expected improvement, which is maximized here at 4.5 or something like that. And the green dot here is the realization that I will get in the future when I evaluate there. So the green dot is the next point. It is not yet part of the data set. So it's not yet part of the fitted surface. Okay, so I'm maximizing expected improvement. This is the point I get next. When I hit return, I will get to incorporate that point. So you can see that point turns black, and my surface goes down to get it, and reduces the variability nearby. It actually reduces the variability everywhere, but the most reduction is nearby. And the potential for expected improvement has gone down too. I've been a little bit careful here to keep the y-axis of my expected improvement constant so that you can see that learning has happened. My potential for expected improvement has gone down. Even still, the next point that I want to take is nearby. It's maximized here at about 4.75 or something. So this is the next point to take. And when I hit return, it will take it. By the way, these are live calculations. This was not run in advance. It's all going on in real time. So you can see it turns around these decisions relatively quickly. The next point to take, the next place expected improvement is maximized is here, which is, we believe that the response is going to be there, but we have a wide interval, and that was right, because look where the truth is, it's low. The function did not stay flat, it went down. And so we were right to worry that might happen. And when I take this point, it's going to dramatically change what we believe nearby. Now the next point I want to take is here. I don't know what the function is going to do. I mean, it could go lower and come back up. I should probably, I know it's a sinusoid, so it's not going to do that. But the Gaussian process doesn't know that. So this is the next point to take. Again, it's where expected improvement is maximized. But now I'm pretty confident that the answer is not over there. But the same thing happens over on the right. Now expected improvement is maximized over here. But I very quickly realized that that's not the case. And I can keep going in this way and keep refining what I believe, but eventually I'm pretty confident that the answer is here.
There's a question.
Yes.
There is a question for clarification.
Sure.
Why isn't the point of maximum expected improvement not always the point with the largest error bars?
That's okay. Because I think that the location matters. So this is the point with the largest error bars, right? But it's nowhere near here. What I care about is an improvement on this y value. Even though these are large error bars, they're far from offering potential for improvement. Of course, there is some non-zero probability of the gray line coming down here, but just looking at this, that looks like maybe like 1 in a billion. Based on, these are 95%, which means another 1, 2, 3, another 6 error bars is essentially impossible, according to the model. So I don't know if that's exactly what you were getting at. It's this expected improvement is not looking to maximize the probability of improvement, which is another thing you could do. But probability of improvement doesn't work as well because it doesn't consider the magnitude of the improvement. The chances might be good that you can make an improvement, but unless it's a large improvement, it may not be worth trying.
I hear that that has clarified the point.
Okay, good.
You're getting some appreciation on Discord for this nice demo as well.
Okay, good. All right. Well, I have one more demo like this, but I'm going to stop this one and go back to the slides. Okay. All right. Hopefully you can see my slides again.
Yeah.
Okay, so that's the demo. So now I want to come back into this horse race, whatever you want to call it, right? We had our surrogate method, and then we had Optim, and then I said we could do better. So that's why we introduced expected improvement. And so I'm going to code up this function, expected improvement, and then I'm going to build it as an objective to optimize. So I want to maximize expected improvement, but I'm going to use an optimization library that minimizes. So I'm going to minimize negative expected improvement. So I can put it into the algorithm so I can run it 100 times, and I can show you the average case behavior on this two-dimensional problem that we were working on. Have a drink of water. Okay. Here's just a little note. I thought about cutting this slide, but you will notice, especially if we go back in time, oh, you can't see this, especially if we go back to this example here, you'll notice that the surface here has multiple domains of attraction, and that could potentially present a problem when trying to find the area which has high expected improvement. You could even say this has a tail, what do we want to call it? It's like, it has a subproblem that's just as hard as the original problem. I set out trying to maximize or minimize a function, and I ended up trying to maximize or minimize a function that had many local minima. I guess with this slide, I'm trying to tell you, don't worry about it. Our goal here isn't to always do the perfect decision. It's just to guarantee that we don't miss anything, that our aggregate decisions over many iterations usually picks the right thing. And so that's what I'm trying to say here. There is a multimodality to the EI surface, but it's not going to be pathological. It'll tend to have about as many modes as the original function does. And we don't need to choose the very best expected improvement location every time. As long as we generally do it right, the algorithm will work really well. Maybe you'll have to take my word for it. So here I'm going to write up a piece of code that does a for loop to search by EI. And I'm not going to go line by line through this. It's just my implementation of the EI search or ego algorithm. And then I'm going to demonstrate it for you in the same environment. So I'm going to start with 12 and fit a Gaussian process, and then do the EI search and show you the decision, I think, here. Okay, so this is the original 12 points. This is the point that I chose by expected improvement. The multiple arrows here are showing you the different decisions you would make if you initialize the EI search differently. So sometimes I would choose this point over here if I initialize the EI search differently. On 2 other occasions, it found the same location. So I'm trying to illustrate that there's some variability in what you might pick, depending on how you choose to optimize the EI surface. This is like sometimes finding this answer here, even though you were supposed to find that answer there. Okay, so that does happen from time to time. You don't correctly maximize the surface, but that turns out not to matter too much. Okay, and then I could do the next iteration. Lots of code on the slide, but I can skip kind of right through it. Again, this is the point I took before. This is the next point I'm going to take. Again, I could have taken that same location, right? The first iteration wanted to take a point there too, but it chose not to. It's going to take this one instead. Okay. Let's do more iterations. We're going to have to be a little bit careful here. Similar simulations is no longer a good measure of convergence. Convergence is going to be a little harder because just because you keep getting the same output doesn't mean there's not another location to explore. So you might want to be a little bit careful about stopping early in the EI algorithm because of this balance of exploration and exploitation that it's doing. It's a little bit hard to know whether it would explore in the next iteration, and that would give you a big bump in progress. So I'm just going to run out for a full 50 iterations. Turns out that works really great anyway. Okay, so here's that one optimization. You can see that one optimization got down to -3. Of course, that was only just one time. And here I'm showing you the largest expected improvement value. Notice how that's bouncing around a lot. This isn't a good measure of convergence either. It believes there's potential for improvement, even though it hasn't made any improvement in a long time. Why is that? Because there's big parts of the input space that it hasn't explored yet. It's still learning about the function. And in fact, the theory that is out there for this algorithm says that the only way that you can guarantee that it works is by letting it keep running and explore everywhere, which is somehow unsatisfying. You want to stop it early, and you want to stop it at 50 or even at 30. But it's saying, well, there might be more stuff to do. I'm making good decisions now, but I can't guarantee to you that I've made the best decisions. I won't know until I've looked everywhere, which is is what it is when it comes to searching the input space. All right, so that was one time. I want to put it in a function of its own and run it 100 times. So that's what these next two slides, I skipped through this slide, right? There's my function, and here I run it 100 times, so I can show you the behavior over 100 random initializations. Now, before I go, I don't want to show you a plot that has 300 lines in it. The last one I showed you had 200, and 300 seemed like a bit much. So I'm just going to show you the averages of the three sets of methods, and then I'll show you the distribution at the end. Okay, so here are the averages. This is the average progress of the three methods. Here's the one we started out with. Here's optim, which was slow by comparison, but still making progress. And here's expected improvement. They work about the same in the beginning because it turns out it doesn't matter whether you purely exploit, but at some point you need to explore or you miss something. You miss those minima that you weren't in. You didn't know you weren't in. You have to explore a little bit so you can jump down and guarantee, all but guarantee that you're in the right global minima. So here I'm going to show you at iteration 50 what the distribution of best value is. Okay, so EI is not perfect, right? There was one example out of the 100 where it hadn't converged yet to the right answer. More iterations would have certainly done it. So 99 times out of 100, it gets the right answer. The surrogate one, this is how to read these box plots. The median is at the minimum, and the rest are above it. So only half of them are getting the right answer. So half of them are getting the right answer. 99 out of 100 are getting the right answer here. And for optim, all but one or two are getting the right answer, or getting the wrong answer. Neither of these will improve if you run them longer. Once they're stuck, they're stuck. They don't become unstuck. This one will eventually get it right if you give it more iterations, but most of them got it right. Oops, what did I do? I jumped to the other slide deck somehow. There we go, okay. Okay, so that's hopefully to convince you that this is a good idea. You can prove things about it, that eventually EI will converge, but only in the sense that eventually it will explore everywhere, which is not what you want. You don't want to wait till eventually. I always hate those asymptotic arguments. This is all about not eventually. The whole point of what we're doing is to limit ourselves to soon instead of eventually. And in practice, it does really well. There's, of course, ways that you can break anything. I think that I know how to break EI. I kind of don't want to tell you how to do it because I think you're going to have a good experience with it. I think it generally does work well. All sorts of embellishments that you can do. Francesco asked about this. You can deal with noisy functions, which is unique, right? There aren't none of the built-in optimization methods in R are able to do that. You give it noisy data and there's no telling what's going to happen. It's probably going to throw an error message that it doesn't understand why it can't calculate the gradients because the data is noisy. But this just works. You might need to change your definition of the problem to be specific about what you want. You don't want to improve upon the best value you have so far because that best value is random. It could be noisy. It could be impossible to beat it because you got a lucky small value that wasn't really a small value. So you might need to change your minimum to be a mean. You want to improve on the best average value or something like that. But the basic idea works just fine. Okay. Now I want to turn to a harder problem. So that's expected improvement. I want to talk about optimization under constraints, which I think is most optimization problems. So hopefully this is going to be a little harder, but hopefully more practical. Okay, so I'm going to first provide a mathematical program to describe what I'm talking about. So now I assume that there are two functions, a function f and a function c. So f is my objective, it's what I want to minimize, and c is my constraint. And c may be vector valued. This is the most common thing is that you have one objective and multiple constraints. So that's what I'm thinking about here. So this constraint function c, to be satisfied, all of the components of its output, let's say it returns 1 or 2 or 3 values of a constraint function, must all be negative for the constraint to be satisfied. So I want to find a solution to this that minimizes f subject to the constraints being satisfied. And there are lots of different ways to do this, but I'm presuming that it's expensive to get both evaluations and that you get them at the same time. So when you run your simulator or your virtual simulation, you get the output of f and the output of c at the same time. You can imagine lots of variations on that, where the constraint is free. So I could, this is actually what I write here. Imagine you can evaluate it as much as you want. And if you could do that, then all you have to do is multiply expected improvement by whether or not the constraint is satisfied. That's kind of a simple variation on this problem, right? If you know where the constraints are satisfied, then you would never evaluate anywhere outside the constraint region because you could multiply by that evaluation before calculating your expected improvement. I think that's a less interesting case. I'm going to be more interested in the case where you don't know if the constraint's going to be satisfied. You have to run your expensive black box to get that information. Okay, so those are what I call black box constraints. I think that's the more common situation. So you can't evaluate this constraint function as much as you want. You have to evaluate it along with the objective and get both pieces of information. Constraints come in many different shapes and sizes. Sometimes they're binary, which still fits into this program, right? It's 0 or not, or they can be real valued. In the case where they're real valued, they provide extra information because you have kind of a notion of distance to constraint satisfaction coming from the output. The larger the number is in positive, the less close you are to a boundary. In that case, you can still do expected improvement as long as you have the ability to predict the probability that you satisfy the constraint. If you have that ability, then you can do expected improvement by multiplying the two things together. You multiply expected improvement by the probability of satisfaction. I'm kind of dispensing with this because I think they're not interesting. They work really well and they'd be easy to try on your own, but I don't want to go through in detail how they work. I do want to go through a different idea that I think is really important when you have lots of constraints. So here, I already said you could have multiple constraints, but I'm talking, this is maybe the most common situation where the number of constraints you have is potentially large relative to the number of objectives that you have. And you could still do expected improvement. You really just multiply by the probability of constraint satisfaction again. So again, another one out of the way. Someday I'm going to change these slides and make it just one slide because I want to focus on an example, a challenging example where I'm going to develop some new methodology for the rest of the segment. So here's an example problem that fits into this framework. Here's the program. This is the mathematical program. So I want to minimize this function. And notice it's a simple function. It's just a sum of the two inputs. So that's my f of x. And I have two constraints. And the two constraints are nonlinear. So these are the constraint functions. I think this is a common situation. This is a caricature of many problems that I've worked on that involve real simulations. The story is the following. You have some expense. This is the operating expense. There's a system with two knobs, knob 1 and knob 2. And the expense in running the system is x1 for knob 1 and x2 for knob 2. And so the expense of operating both of them is the sum. But what you don't know is whether operating the system in those conditions is sufficient to satisfy the goal. So I worked on a problem that's exactly like this, and we talk about it in the book, where there was a remediation exercise. There were some contaminants underground, and they were going to build wells and pump water into the system in order to diffuse the contaminants. And they knew that if they pumped more water through the wells, that would help more. The more water they pumped, the more likely they were to get rid of the contaminants. So they knew they could satisfy the problem with a large expense, and they knew what that expense was. There was no simulation required to determine how expensive it would be to pump water. What they didn't know is what the right amount to pump was to solve the problem. And so under the hood, there were constraints, and those constraints were hydrology simulation experiments. They were modeling the rock underground and pushing water through the system and trying to work out whether or not they could get rid of the contaminant. And the response surface was highly nonlinear like this one was. So the constraints were what was expensive and was unknown because it involved a complicated hydrology model. And the function they were trying to optimize was easy, but it was still a hard problem to solve. And it was the constraints that were making it difficult. So here's a little picture of this problem. Again, this is not in R code, so it's just captured it from the paper, but we'll look at an R code version of this in just a minute. So the unconstrained solution is at the origin. Just put zeros in for x1 and x2 and you'll minimize the function, but you won't satisfy the constraints. The two constraint boundaries are the black lines. This is C1 and this is C2. It's clear that different values of the inputs are required for satisfying the constraints, in particular for C1, because C1 is really important. All of the local solutions are on the boundary of C1. None of the local solutions are on the boundary of C2. C2 is what they call a non-binding constraint. And the gradients here are the objective. The objective is linear, so you clearly want to be as close as possible to the binding constraint. And the best of these three local solutions is the blue one. The blue one is A. It gives the smallest value of the objective, which is 0.6. So this is a difficult optimization problem because it has nonlinear constraints, not because of its objective, although you could have a hard objective. Even with an easy objective, it's a hard optimization problem because there are multiple local minima. Okay, so before telling you about how to use surrogates to answer this problem, I want to tell you about how the optimization community solves this problem. And they have lots of really good ideas. Part of my own research in the last 5 or 6 years has been to learn about how people have solved these problems before with ordinary optimization methods and find ways to put surrogates in there, to put them in the mix, to get a probabilistic notion of improvement, like expected improvement, and use it to trade off exploration and exploitation. So let me tell you about how one way that math programmers would solve problems like this. So nonlinear black box optimization problems under constraints. They have great methods where they can prove convergence. They have lots of software. So it's really hard to compare well against them because they do so many things right. In statistics, in machine learning, whatever you want to call it, we have nice global optimization algorithms. And we do really well when the simulations are expensive because we do this trade-off, but we don't have good methods for handling constraints. The 3 ideas I gave you before are fine, but they're like the only 3 ideas. And they don't use any of the stuff that people have been working on for a long time. Okay, so one of those frameworks is called the augmented Lagrangian. The augmented Lagrangian is a souped up version of what you might think to do on your own. That's why it's such a cool idea. So why do I say that? So the augmented Lagrangian creates an auxiliary function called L, called the augmented Lagrangian. And it takes the original function and it adds to it the constraints. In fact, if you look closely, it's basically adding the square of the constraints to it. Although in the case where the constraint is not violated, it adds nothing. This makes sense. You're kind of creating a hybrid, right? You're saying, I want to minimize this, but I get a big penalty if my constraint's violated. So I want to avoid that. I'm going to hit that with a square. And that's going to push me towards the parts of the input space where the constraint is not violated. So I can just focus on the objective. There are more terms than just the objective and the constraint squared, though. There's this 1/2 rho, and there's this lambda c. The lambda is the Lagrange multiplier. Lagrange multipliers are how we solve optimization problems with calculus, right? But we don't have the derivatives, so we have to be a little bit careful about how we do it. So I want to create some kind of Lagrange multiplier thing, and I want to penalize the constraints. But I put this apparatus together. Why? Because you can prove things about it. You can prove things about the sequence of Lagrange multipliers that you get and so on. I'm not an applied mathematician. I'm not going to try to explain to you except on the level that I understand it. It's got objective, it's got constraints, it's got Lagrange multipliers, and it has an algorithm for setting those parameters, for determining what the penalty parameter should be, for determining what the Lagrange multiplier should be, in order to come to a numerical solution that minimizes the objective and satisfies the constraints. So the augmented Lagrangian methods transform a constrained problem into a sequence of unconstrained ones, or they would say simply constrained ones, because we're still constrained by the study area that we're willing to search in. You can drop the augmented Lagrangian, you can drop the Lagrange multiplier term if you want. You can drop the 1/2 rho if you want. And you get the intuitive idea of the additive penalty method approach. But that method doesn't work very well. These extra couple of parameters, if chosen correctly, make the algorithm converge and let you prove that the algorithm converge. But it's not just about proving it. It's about it working well in practice too. So here's the algorithm. It's a really short algorithm. It says, choose some settings of those 2 parameters and solve the problem. Minimize the composite. And then take the answer you get from that and use it to update the parameters. The 2 parameters are lambda and rho. Basically, you make lambda better if you don't satisfy the constraint, and you make rho smaller if you do. So you kind of adjust these parameters in a big loop. You solve a subproblem, which is an optimization of a composite, a constraint-free optimization. and then you change the weights on the things in the augmented Lagrangian, and then you repeat. So this is the outer loop, and this is the inner loop. An important thing to note is that the functions that are expensive, these are expensive black boxes. They're only involved when you're solving the inner subproblem. So the expensive evaluations are in here, not in the outer loop. Okay. Let me show this to you in action. So I said I was going to go back to R and do another demo. This is going to be clearer, I think. Okay. So let's unshare and then share again. I think you can see my R session. I'm bringing up a different file. Okay, so I will show you some of the code on this because I think it's elucidative, or it's gonna help you understand a little bit. So here's that function. This is the one that I put up on the slides. Simple, objective, nonlinear constraint, nonlinear, non-binding constraint. So that's the problem. I need to wrap it in the augmented Lagrangian. So I evaluate it, and then I put it into this linear combination. It's the function f plus Lagrange multiplier times c plus penalty parameter times the max of 0 and c squared in a sum. So this is my implementation of L. So original problem, Lagrange multiplier version. Okay, bounding box is simple. I'm going to do something over and over again. What am I going to do over and over again? This is all plotting. I'm just going to initialize my lambda row to something, make a plot for you. We'll see those plots. And then I'm going to do a loop. I'm going to solve the subproblem. I'm going to optimize the augmented Lagrangian inside of an optim command. And when I get the answer, I'm going to update the augmented Lagrangian. The rest is plotting. So the most important lines of code are these two and this one. It's basically a 3-line program, 4, maybe 1, 2, 3, 4. This is all just plotting. Okay, so let me source this for you and you'll see what I mean. Oops, I just sourced. I'm going to quit this one first. Get out of here. I want to source this one now. Okay, I'll make this a little bigger. So I've plotted the constraint surfaces. This is the first one. This is the second one. Remember, the unconstrained answer is here at 0, but I've got to be inside this region here. I've randomly initialized. This is my first point, just picked randomly anywhere. And then I'm going to step through the iterations of the algorithm. First, it's going to optimize with whatever setting of the initial setting of the parameters is, and then it's going to update. So I do it one time. It did the optimization, and that's where it took us. And it updates the parameters here. It's in this part, and then it's going to do the next one again. It's going to update again and do the next one. Update again and do the next one. Update again and do the next one. You can kind of see that it's focusing in. I've stopped the algorithm a little early because I want to show you multiple evaluations. Now, inside of this optim, it's calling the augmented Lagrangian. And inside the augmented Lagrangian, it's calling the expensive function. And in fact, it did that 167 times. So it had to evaluate the expensive function 167 times, even though it only did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 loops through the augmented Lagrangian method. So it's quite expensive. Solving this problem, even locally, even starting here, required a lot of evaluations of the expensive function. When I press return, it's going to repeat with a new random initialization. I colored the points black when they're in the satisfaction region and red when they're not. Okay, this one, same algorithm. You can see it's converging to a different spot. And it evaluated the expensive function 139 times. So so we're not getting a global solution, but we are getting it's a good solution. This is one of the local minima, but it's taking a lot of evaluations, repeating. Okay, same local minima. It's kind of fun to see what happens depending on where you initialize it. Okay, so sometimes it's intuitive. This one kind of went that direction. The two over here went that direction. The one that was here went this direction. Which one's that one going to go to? Oh, okay, that makes sense. It's going to that one. It's nearby. Okay, where's that one going to go to? Well, maybe that makes sense. It's going to that one. Where's this one going to go to? I don't know if that one makes sense to me, actually. It kind of looks geographically like it's closer to this one. But I guess because of the way the surface was going, it decided to go this way.
We have a question on Discord on a clarification about why x1 and x2 are between 0 and 1. How is that? Is that a constraint or is that a setup of the variables?
It's a setup. So that's what they might call the bound constraints. It's just in the definition of the problem. I want to find the best x1 and x2 in this hypercube between 0 and 1. That's just how I define the problem.
Could you clarify where you said that bound constraint?
In the code, let's see. Here, the bounding box is here. So B, if I just quit out of here, escape.
I guess to clarify my question a little bit, if I could, yeah. Bobby,
Sure.
Could you set up, additional, I guess it would be 4 additional constraints, or maybe think of it as 2 additional constraints on x1 and x2 to be in that box rather than doing it in the setup? You could do it the same way as your let's call them curvy constraints.
Yeah, I guess you could, but I think that for the method to work, you would still need to specify bounds on something. Like, for example, when I do this inner solver, I'm giving it the bounding box, telling it I don't want a solution outside of there. I suppose I could put minus infinity to infinity. That might work. A lot of these built-in subroutines do not work as well if you don't give it bounds. I'm not sure what would happen, I think is my answer. I think it's fine from a theoretical standpoint, but the implementation...
It's just a practical implementation issue, yeah, okay.
I think so. Okay, that's about all I was going to do on that. What were the takeaway messages from this? I think I'm going to stop sharing. I think I've got that in a slide, so I'll bring up the slides. Okay, mostly got it in this slide. So the augmented Lagrangian algorithm is, you can prove things about it. You can prove that it will converge locally, but you've seen in this example that it does not converge globally. In fact, sometimes it's hard to predict predict even which of the solutions it's going to find at the outset. Sometimes you can look and tell, but other times, even when you think you can look and tell, you can't. And they do a lot of evaluations of the black box function. So those are 2 downsides. Upsides are that you don't need to solve the inner subproblem exactly. In fact, as long as you can guarantee that you make some progress on the subproblem, you can show that the algorithm will converge. So it's robust in that sense. There are a lot of examples in the optimization literature that are like that. In statistics, we like to talk about the EM algorithm being like that. I don't know if that means anything to you or not, but the EM algorithm is an optimization algorithm where you don't need to solve it exactly in order to prove that it will eventually end up in the right place. So the augmented Lagrangian is like that. As long as you can make a little bit of progress in each inner problem, you will eventually converge. So that means you have some flexibility about how you solve that subproblem and about how you maybe use a model like a Gaussian process in order to help with that decision. So that's what I want to turn to now. So I want to develop a statistical inner solver. In my demo to you, the inner solver was Optim using the Nelder-Mead method, which is a popular optimization method that doesn't use derivatives. But I want to fit a Gaussian process, and I want to use expected improvement or something like that instead. So the idea here is to take all the data. Here's the data. As the algorithm is running, I'm choosing inputs to run, and I'm getting evaluations of F and evaluations of C. And I'm forming a data set. And I can collect that over all the evaluations. If I'm doing an augmented Lagrangian, every time I evaluate it in one of the inner loops, over all of the outer loop iterations, I'm gathering data. The augmented Lagrangian method that I coded up and that most people would use is not saving any of that stuff. It's kind of memoryless in that respect. It's always just making a decision based on where it was a moment ago. It's not taking all the data into account. And I want to do that. I want to fit a Gaussian process to those data and use them to choose the next point. And I hope is that when I do that, I can get a global solution and I can get it with fewer evaluations of the expensive black box. So here's how one way you could do it. There are many ways you could imagine doing this. I hope that you're seeing possibilities as we go through and understanding that what I'm showing you is just kind of one, maybe easy to describe way of doing it. So I'm going to fit a Gaussian process to each thing. I'm fitting lots of Gaussian processes here. So I'm going to fit one to the objective, and I'm going to fit m separate ones to each constraint. So in my toy problem that we were going through, there are 2 constraints and 1 objective. So I could fit 3 Gaussian processes, 1 for each. Or I could treat the objective as known and not fit a Gaussian process for it at all, and only fit it for the constraints. Either of those things would work. And then I'm going to take those fits, so YF and YC1 up to YCM, I'm going to take them and define a composite, borrowing from the augmented Lagrangian. So this is the same formula we had before, but all of the Y's are random variables. Each one of these Y's has a distribution. This one's Gaussian, and this one's bivariate Gaussian, because there's 2 of them, and each one of these is Gaussian. And together, although I'm writing this down, it's not something that I can really compute because it's a random variable. It has a distribution. And I want to work with that distribution. I want to define its mean, or I want to calculate its expected improvement. And it turns out you can do both things. So its mean has a closed form. You can calculate the expected value of it. So you can figure out what the mean of the augmented Lagrangian random variable is. And you can use that to drive optimization. You can take the next point to minimize it, say, if your goal is to minimize the function, subject to the constraints. And there's a formula on the slide that shows you its form. If you want to do expected improvement, it's a little harder. You can also do it in closed form, but I don't want to put it up on the slides because it's a bit of a distraction. If you want to figure it out, you can click on this link here. But the idea that I introduced earlier also works well. You can do Monte Carlo, and it's actually faster than doing it in closed form. You can just take samples from these YFs and YCs and average them, average their improvements.
Just a quick heads up that we are approaching the lunch break for.
Oh, is it 1:15?
Yeah,
okay.
You can. There is some slack.
No,
so
I don't want to do that. I don't want to do that. I think we'll just look at some results. It works. It always gets down to the right answer of 0.6 every single time. So I'll leave it to you to play with that. I definitely don't want to go over. You can look at some really cool problems. Here's a hard optimization problem. So I replaced that the simple objective with a complicated one, and it finds the right answer. You can make it find an even better answer sometimes. We've done this with really hard constraints. These are equality constraints and inequality constraints. So really cool stuff. I'm going to stop there. The last thing I want to do is be that guy who eats into your lunch break. Let me just end by saying thanks. Thanks for the invitation. Thanks for the great questions. It was great to be a part of this.
Thank you for joining us. This has been really marvelous, both the intro to GPs and the surrogate modeling. Thanks a lot.